Okay, good morning. I'd just like to thank the organiser. I'm not a regular attendee at PDEs on a Sphere, so it's very nice to come to this sort of meeting, and it's a fantastic meeting. I'd like to thank the organisers very much for letting me have a talk. So this is a slightly different way of testing numerical schemes, so it complements what you've been seeing a lot of already, and I hope the fact it's a bit different will be of interest. We've got to remember in the problems we're actually doing, there's absolutely no way we're solving the equations we've written down correctly. If you think about compressible Navier-Stokes for the atmosphere, there's nothing particularly insoluble about these equations. If you're an engineer and you're looking at a very small region, you just solve them with a standard solver and the answers are fine. But to solve them correctly in the context of the global atmosphere, you need 30 orders of magnitude more computer power than we've got now. And then you can just imagine what the power consumption of this computer will be when it's available, probably like the output of the sun or maybe the entire galaxy. But anyway, it's not going to arrive just now. And that means that instead of just, if we could resolve the solution, it's really down to the standard numerical analysis of accuracy and stability, and that's enough. But since we can't resolve the solution, you have to think, well, what are we actually trying to get right? And if you think back to the beginning of the meeting, particularly John Thewburn's talk at the beginning, some of the other talks the first morning when they're talking about mimetic properties, they're really trying to think, well, what are we actually trying to get right? It's not simply a matter of accuracy. And these tests are really a way of trying to be quantitative rather than, say, having gut feelings about what you want to try and get right. This is trying to say, well, how much do these things actually matter? And can we sort of show that we're achieving them? So what we do is we look at flows that we can resolve and relevant things we worry about for weather and climate prediction, and mathematical theory tells us that these can be accurately described by asymptotic limit solutions. In other words, they are to some degree of accuracy, they're solutions of simpler reduced equations as well as being solutions of compressible Navier-Stokes. And the obvious example is that when you're looking at extratropical weather, the flows you're interested in for the weather are primarily described by the semi-geostrophic equations, which are based on geostrophic balance. As we now move to higher resolution, we get interested in more different types of flows as we can start resolving more things. And for instance, we might want to find such solutions describing gravity waves, which again, people are very interested in predicting gravity waves, and our resolution is now getting towards being able to do that on some occasions. So the mathematical basis of this is the theory that the solution of full equations like compressible Euler or Navier-Stokes converges to that of suitable limit equations at some rate order epsilon to the k, where epsilon is a small parameter. It might be a bit more complicated than that. It might involve several small parameters converging to zero in a prescribed ratio. And then you can say, well, this is true of the full equations. Can we say that our numerical model converges at that rate as well? Because if so, you'll say, well, it is, let's say, sufficiently geostrophic to match what the full equation should do, because you don't want to say it should be exactly geostrophic, because that's never going to be true, except in some trivial special cases. So you're applying a test which should be satisfied by a genuine exact solver of the full equations. Now, on the face of it, the obvious way to do that is actually to compute the limit solution directly and compare the difference as epsilon tends to 0. But sometimes the limit solutions may be much harder to compute than that of the full equations, because in some cases they involve implicit coupling between variables, and the condition number of an equation with a strong constraint imposed, like geostrophy, is much, much higher than that even of a, say, semi-implicit solver of the primitive equations. So you may make such a bad job of solving the limit equation that it's no good as a validation, in which case it's better to test this by calculating appropriate diagnostics, which obviously means you can just use your model results directly. You'll see both shown in the talk. At the moment, it's very important to do these tests because existing methods we've got used to are being challenged on the grounds of scalability, and it may be that semi-implicit methods, which we think will be better at some types of flow, don't actually show they're any better in this sort of test, in which case we'd like to know. So we'll start off with a shallow water example. So if you take shallow water and its depth is h with mean value h0, linear gravity wave speed is that. And the Froude number is the ratio of your typical flow speed to the gravity wave speed, so that's the Froude number. And as you let the Froude number tend to 0, which means letting the depth of the water tend to infinity, the solution will converge to that of the 2D incompressible Euler equations as a rate epsilon, order epsilon squared. So this is a nice sort of standard obvious thing to test. So my demonstration, I'm going to use the methodology dynamics code, which is semi-implicit, semi-Lagrangian on a C grid, and probabilistic variables, because it's a code for the use in the main model and not vorticity, but depth and the components of the velocity. And in this case, I can compute the limit solution, because if I have a semi-implicit model, I can just fiddle the Helmholtz equation to force it to say div u equals 0 at each time step. So here I can keep the numerics exactly consistent, and I just tweak the Helmholtz equation. Now in doing this test, you find very quickly that it's really critical how you initialize the models. So, and I found the best thing to do, having discovered certain things you shouldn't do, you get the discrete vorticity identical. It has to be the discrete vorticity, not analytic vorticity, and the orbital velocity is set to have 0 divergence at t equals 0. And then I'm going to demonstrate the RMS errors in h and vector velocity off. And these tests are done at a fixed time for different choices of mean depths. I'm not looking at different times, you can obviously do that, but I'm letting the depths tend to infinity and just repeating the test. So that's just some of the parameters of the Froude numbers, so in the range 0.05 to 0.3. And now here are the RMS errors for vector velocity. And it should be second order, and you see this is not a log-log plot because, for obvious reasons, it doesn't hit 0. And you see it's going down a sort of second order rate, but it's sort of trying to asymptote to something that's definitely not 0. And the depth is really getting stuck at quite a much larger error than that. So it's sort of working, but it's not quite right. And you think, well, you'd hope to have done better than that, because the numerics of the two models are identical. You're not looking at different numerical errors, so what might be going on? So what's probably happening on the biggest problem was initialization, but I can't think of any better way to do the initialization than the one I used, having tried a few others. But the implied vorticity equation that's determining the limit solution is horribly discretized, because remember, this is a model working in terms of velocity components. And if you work out, and the velocities are stored on a C grid, which is not ideal at all for representing vorticity, and almost certainly this is a poor implied discretization of the vorticity equation. It's a bit easier to understand the poor results in convergence in depth, because in the limit, the depth is just a diagnostic. It plays no part in the dynamics at all. It's pure vorticity dynamics. So it's not very surprising the errors are not well controlled at all. Now, if obviously you want to win in this test, you use a scheme with vorticity as a variable, but you might not want to do that. Now, the next example is a frontogenesis example. Now, in order to do this test cleanly, I use an incompressible Boussinesq equations, and the reason for that is to make sure that the 2D vertical slice model I'm using for the test satisfies appropriate conservation properties. Because if you extract a 2D model from the compressible equation, it doesn't actually conserve anything because of the nonlinear equation of state. So by the idea then is to use the numerical method for the incompressible model, which is the same as you would use for a compressible model. So just to show you the equations quickly, but I think we'll just, this is standard vertical slice model. It's non-hydrostatic and incompressible Boussinesq. And it's now the small parameter is the Rossby number, and the limit solutions of the semi-geostrophic model, which is, because of the geometry, second order accurate for all situations. That's an artifact of the geometry, and that's obtained by throwing these two terms away here. So that reduces geostrophic, and that reduces to hydrostatic. Now in this case, we know the limit solutions exist, but the limit solutions are discontinuous, and nobody knows whether the solutions of the Boussinesq equations are discontinuous or not in this geometry. I think most people, a good educated guess is they're probably continuous. So you've got a situation of continuous solutions converging to a discontinuous limit, which is obviously going to be quite challenging for numerical methods. Scale analysis says that SG is always accurate to order epsilon squared while the solutions are smooth. It's not clear whether that will be true when the solutions are discontinuous, because typically you can't converge at more than first order rate to something that's not smooth. So, and then the incentive for this test is a solution of this problem in the limit, which has some very appealing quasi-periodic behaviour, which is sort of, you feel this is a nice model of extended range life cycles, and it conserves energy very well. It just oscillates and it goes, and if you perturb the numerics you get almost exactly the same answer. So I feel this is a very good test for the long-term behaviour. And if you run it with a standard numerical, well, it's run with standard numerical models a long time ago, and the sort of answer you got was this. You got through, matched reasonably well at the beginning, except there was far too little energy, and then but it just gradually lost it as you went on, with things just too diffusive. If you look at a typical solution, this is from the Bucinevsky equation, so it's not a balanced solution. You see that very strong fronts form the upper and lower boundary, but some gravity waves escape from where there's a scale collapse. And then the challenge is to show the gravity waves disappear at the correct rate as you take the limit. The other thing is the way you take the limit ensures that the balanced solution with the front is not affected, so you effectively compute with different Rossby numbers in such a way that the front stays exactly the same. So the gravity waves should change and gradually disappear, but everything else should be identical, so it's quite a good test. So initially demonstrate using linearized equations that we get the right limiting behavior. So this is not the full nonlinear problem. We're looking for second order convergence, which is that line down there. And if we use a fully implicit, fully decentered scheme, this is showing convergence at different days. So this is Rossby number, effective Rossby number along the bottom. Different symbols at different days through the integration. This is all, well, this is the linearized problem, so it stays smooth anyway. You'll see we very accurately reproduce the convergence to the limit. However, if you don't decenter, so you use purely centered implicit schemes, you find that you start going off the convergence line. So these 10 to the naught beta, that's a sort of, if you like, a standard atmospheric parameters. That's the sort of parameters you'd actually have in the real case. And this is sort of pushing you towards smaller Rossby numbers. You find you start losing that solution quite quickly. So that's saying it looks like you have to have some damping of the gravity wave solutions to obtain convergence. Now these are the extreme cases. This is exactly centered. This is fully decentered. So a Bede who's done this work, is sitting in the audience, I hope yes he is, has also found that if you just use a decentering parameter of 0.55, you could actually hold this line all the way down. I think 0.51 didn't quite make it. So it looks like you have to have significant decentering, but nothing like full decentering. Now, in the nonlinear problem, we haven't got the results using the incompressible code yet, so I'm going to show you results from the compressible slice model. And we can only use this for the initial frontogenesis where the lack of conservation doesn't matter. We can't use this test to go through the multiple life cycles. So I'll just... and what we're doing here is because in this case it's extremely difficult to compute the limit solutions using conventional numerical methods, and think that to do this test successfully you need consistent numerics in the limit model as well as the primitive full equations model. So here I've used a diagnostic test. In other words, I've calculated the geostrophic imbalance for different values of the Rossby number, and I want to make sure that tends to 0. And my other checks of convergence, I take the lowest Rossby number I can run with, and I pretend that's got epsilon equals naught, and I compare the other solutions with that. That gets around the problems of computing the limit solution, which is very difficult in this case. And obviously, if you think of something more complicated, you nearly always want to use a diagnostic method to check the convergence. So this is the convergence of the wind along the front at different times, and this is with fully monotone semi-Lagrangian advection, and this is with just high order semi-Lagrangian advection with no limiter. And in this case, the earlier times, days 3 and 6, are really before the front forms, and you can see second order convergence in Rossby number. But at the later times, the front has formed and the convergence rate drops to something like first order. If you don't use the monotone switch, you can't make it to day 9 without adding extra diffusion, so that's why it's day 8. and you can see these convergence rates still there. It's just the value of the difference. Well, whether you call it an error or not, is you have to sort of think, well, how big should this difference be? It's not, it's not necessarily that the lowest value is actually the best solution. You have to go away and think, well, what's the right value? But the convergence rate is quite clear. You've still got the right convergence rate. It does reduce when the front forms. And you can apply that test to the potential temperature as well. Much the same message. Reduce convergence rate when the after the front forms, which may well be optimal. You probably can't expect to have second order convergence for the discontinuity. And this is the imbalance test. So this should go to 0 as you go towards the limit solution. And again, it does to second order rate. The values of the imbalance are somewhat lower with quasi-monotone advection. Again, you'd have to do an estimate to say, well, what you think are the right values, because this might be converging too closely. You can get this test wrong in both directions. And similarly, reduce convergence rate after the front forms, and as you see on that plot. So that's all. We haven't. This version of the problem can't be taken beyond the initial frontogenesis because of the lack of conservation. So we're waiting for the nonlinear runs with the other code, which is the incompressible code, which we can take through the front, and see if we can get a better answer for the multiple life cycle. So it summarises that bit. Right, now I want to spend a few minutes on this one because nearly all the tests we're looking at are purely tests of adiabatic models, and it's almost certain a lot of the errors in numerical models are due to, well, the physics is a very complicated single column calculation, which has been very well validated on its own. The dynamics have been very well validated on its own, but the coupling and the way the two fit together have not hardly been validated at all. So it's really important to start extending this sort of analysis to cases where there's physics. Now, what I'm going to show here is just a sort of little toy attempt at it, and I'm hoping in the talk in a couple of weeks' time to have some results with a genuine boundary layer scheme. And I was going to have a 2D slice model with a proper boundary layer scheme. This is just results from 1D shallow water with no rotation and friction, but in a shallow water model it's easy to put friction in as just a Rayleigh damping, so you have a definite frictional time scale, and also a small parameter u tau over L, well, it's the ratio of the effective time scale to the frictional time scale. And now the limit equations are now going to be a sort of Darcy balance between the friction and the pressure gradient, and if you go through the analysis, it's almost impossible by the techniques we've thought of to create something that's second order accurate in that limit and has a negative definite energy tendency, because there's no point having a limit solution whose energy blows up, because that will just, scaling won't be sustained in time. So we haven't managed to think of anything that's more than first order accurate, but at least that's a rigorous test. So, so this shows the result of that test. We've used sort of, I haven't got time to explain models in detail, but this is a sort of semi-geostrophic type model. Obviously it's not geostrophic, it's the friction that's taking the place of geostrophic balance. This is sort of analog of the planetary geostrophic model, where you simply replace the momentum by the amount that you need to balance the pressure gradient and use that in the mass equation. So it's like planetary geostrophic theory, but again in a different context. And this is the sort of the equivalent of the ageostrophic winds. It's now, but it's not ageostrophic because it's the wind that you compute, assuming that the momentum satisfies a balance between friction and the pressure gradient. And that's first order convergence, which all you can expect. This is second order convergence, and we're actually doing rather better than first order for some of these parameters, which is quite good. And we'd like to say, I'm hoping in 2 weeks' time, Bob Beer at X2 I'm working with on this, will have some results using a genuine boundary layer scheme, which is a fundamentally different game from this, unfortunately, because the way the real friction interact is so much a function of the actual state. It's extremely non-linear problem, and you can't just write down a simple frictional time scale, but of course that's the problem you actually have to do. So this is just an advert that we really need to get into more of this sort of thing. So in this case, results are better than expected convergence. Obviously numerics in this case was trivial, so it's more a confirmation of the analysis. and the real interest is taking this to a 2D vertical slice with a genuine boundary layer scheme as in an operational model. Okay, so I think that's it. So
questions for Mike?
Like if you take the actual differential actual problem of the modeling, they are not mathematically closed because of the parameterization.
So what we'd be doing here is we'd be assuming that we have a correct way of describing the boundary layer. So you'd just be taking that. You have to prove that that choice of model could be solved. So you can't do anything about the fact whether it really is a correct model of the boundary layer or not. But you'd assume the physicist has done their job. You've still got to write down a mathematically well-posed equation, otherwise you can't do the test. And in the case of the boundary layer, that's a serious challenge actually with most schemes. And then you can do the test.
In the limit of incompressible flows, the pressure is defined to within a constant. So when you converge, you could have a systematic bias.
No, I don't think that was true. I don't think that was true in this case. But I mean, the problem is the convergence result really applies to vorticity. If you actually look at the way you calculate the convergence rate, it doesn't really control the pressure at all well. So I'm not surprised. And then you can see from the velocity convergence, you still weren't really getting it right. So it's not surprising the results are much worse for the pressure than the velocities. And then you've only got to look at the way you discretize the vorticity equation, and not too surprising really.
I'm new around here. One of the things that I've had my nose rubbed in over the last few days is the extent to which people talk about tuning models and having models that are based, whose fidelity is based on what mesh spacing we use. I'd like to know if you think that there is a weaker question that can be answered systematically than the one of, yes, can we converge the Navier-Stokes equation? Obviously we can't. But can we at least come up with, is it going to be feasible to come up with a model in which you can have a meaningful notion of grid convergence for atmospheric systems, large-scale atmospheric motions?
Well, the reduced models should have resolvable solutions, so you should be able to compute those correctly, and then you should be able to, the philosophy of this is you show that your model of Navier-Stokes converges to those solutions, and that's a pretty rigorous test. It's something you should be able to pass even though you haven't resolved the solution of Navier-Stokes in general. So in that situation, the solution of Navier-Stokes becomes much simpler than it normally is. We want to think of it like that. So I'm trying to apply a test that accepts you can't really solve Navier-Stokes.
Okay, let's thank Mike again.